I'd like to introduce our 2025 Albert W. Johnson Lecture recipient. This year's lecture is paving the way for a new era of human space exploration and hoping to see humans land on Mars in his lifetime. I'm going to show you a short video about this year's recipient and distinguished professor of aerospace engineering, Dr. Ping Liu.
The goal of my research really is to advance the necessary and much needed technology for space exploration, particularly human space exploration. And I think this is something that has tremendous values, both in terms of economical and national security, as well as inspirational. I'm just proud and happy to have this opportunity to work on that and at the environment like San Diego State University. We are working on some of the cutting edge of space exploration activities this nation is embarking on. Through the years of hard work and this is a collective effort, we are at the point where we have very good confidence the algorithms that we develop will perform very well, accurately, and reliably in guiding a mission for landing humans on Mars. How exciting and how difficult it is to land a human on Mars. That is something that no nation has ever attempted. Faculty and students at this university are working diligently trying to develop technology and making a contribution to that final goal. I believe the work that we are doing will directly benefit the eventual success of landing human on Mars, and that is what motivating us and driving us every day. And we are extremely proud to be part of that.
Okay. So first, you can easily see from the video why Ping was selected as our distinguished professor for this year. And before I allow him to come up and speak to us, I'm very excited about this talk. Him and I debriefed about it before he started putting it together. It's really focused. You'll see how exciting it is, and how we'll eventually land humans on Mars, ideally. But Ping is truly a founding leader of the field within aerospace engineering, on computational guidance and control. His algorithmic method for calculating safe landing trajectories for spacecraft in real time is the industry standard, praised and applied regularly by NASA and space industry engineers. So when we say these are people who do transformational work that impact the world, we truly mean it when we select these recipients. So NASA's Johnson Space Center, during the leadership of SDSU's alumna Ellen Ochoa, bestowed him with an innovation achievement for his work. And his algorithms are the prime methods planned for spacecraft missions, Uranus and Neptune. His publications are some of the most consistently cited in his field, and he regularly ranks in the top 10 of authors in his field. He passes on his expertise as the editor-in-chief of the second largest journal published by the American Institute of Aeronautics and Astronautics. While balancing his responsibilities as department chair, which is a huge role by itself, and increasing the reputation of the aerospace engineering program, he's garnered millions of dollars in research funding, even outcompeting faculty at Harvard, Hopkins, and Purdue for critical NASA grants that support the Artemis program. Ping's work is a phenomenal example of the translational applied research that distinguished San Diego State University. So on behalf of the university, I'd like to thank you, Ping, for your contributions to your field, to humankind's curiosity and to this institution. Congratulations. Do you want me to turn it on? Oh, he's set up. Okay, got it. Move all of this up.
The goal.
Here we go. Thank you, Sarah.
Well, thank you, Ella, and thank you everyone for being here. This is a tremendous honor to be the recipient of this prestigious award, and especially in front of so many previous awardees, and feels extremely fortunate to be part of this eminent group. I have to admit, when I started preparing this lecture, it's not without some trepidation, because the past lectures, covers education, health science, even engineering. My colleague Chris Mee talked about wireless transfer power. These are topics that everyone can relate to. Look at the weird topic that I'm talking about here. And, well, it's an obscure job. Someone has to do it. And here we go. So we are inspired to land humans on Mars. And somehow it's got lost in translation. And if you look at the title on the printout, it says many humans on Mars. Someone got very excited, thinking we need to land more humans on Mars. But we'll start with a few. So I will be focusing on three main points. So why do we do human mission to Mars? And my work focus on many challenges for that endeavor. Refers to entry, descent, and landing. So we'll talk about the challenges, and then we'll talk about what do we do at San Diego State to address these challenges. So, just like a movie promo, so we'll start with some sort of short video to get everyone focused. So this is how it all begins. I don't know how to, here we go. So we have arrived at Mars. Then let's go back one step to ask this question, why do we pick Mars? Well, the answer is actually very natural. Mars is the planet next to us. It's the fourth rock from the sun. That's this guy here. This is us. So in terms of size and the mass, it's one of the planets in the solar system that's pretty close to that of Earth. And Mars has water, not had water. It's not just underground ice and permafrost. It actually, we believe it has liquid water. And past Mars climate, believe it or not, was very much like the Earth's climate. This is a picture that was drawn based on the radar data that from a rover, Mars rover, that a Chinese Mars rover was determined just last year in 2024. This is what the ocean at Mars used to look like. And believe it or not, you have a beach, you have ocean there. And there's compelling evidence that there was life on Mars. So all this is very intriguing, not to mention that's close to us. So that's why Mars is our prime target. Here are the few facts about Mars. You can take a quick look. And this is not a very forgiving environment, but it has the largest mountain, largest canyon, and largest dust storm in the solar system. But that's what it is now. So why do we want to do a human mission to Mars? Human mission to Mars has always been in this profession, we call that really it's a holy grail. It's the ultimate achievement if we can land a human on Mars. And a human space mission in general would have what I call three pillars that are the underpinning of this endeavor. Science, the pursuit of science and exploring and understanding the universe, and that's an integral part of the human space exploration. Human space exploration teaches us about the ancient history of the solar system, the environment, human and plant physiology in harsh environment. How do we mitigate engineering and health risk? How do we perform complex operation in harsh planetary mission environment, and much more. And the second pillar is a national posture. Human space exploration establishes this sort of a technology, science, innovation that and national competitiveness that supports growth and global position. Few probably outside our field even know this. Just give you an anecdote. The phrase, the terms, software engineering were crafted in the Apollo program when they were doing the guidance and navigation program for the Apollo spacecraft. Before that, there was no such a word, software engineering. Just give you an idea how the impact have penetrated essentially in all sorts of science and technology. And think about telemedicine and food standard safeties. These were developed for long duration human space exploration. And also think about the national security implication, right? So all this is very much embedded in the national posture. The third pillar, inspiration. As many of you either experienced or have at least heard, the Apollo program inspired a whole generation of engineers, scientists to pursue visionary work. And there's nothing that inspires more than human space exploration. Really, this is the human nature. The human curiosity for the stars has are not limited by race, ethnicity, socio-economical backgrounds, even political persuasion, national boundaries. That's just a human nature that we long to know what in the distant star. So why do we have to do a human mission? Well, it's just simply the case, no robotic, it doesn't matter how many robotic rovers that you send, it can never ever replace a human being setting foot on Mars in terms of that inspiration, right? So that is why we're doing that. Okay. Now, we know we have landed rovers on Mars. That's hard. Landing human on Mars is going to be harder. Okay, give you a simple example here. This is a picture that shows, the past robotic rover mission to Mars. Up to now, let's see. You see those across? These are the missions that had failed. Over 45% of robotic mission to Mars landing mission had failed. In fact, until 2021, US was the only country that has ever successfully landed rovers on Mars. In 2021, China became the second country that has successfully landed a robotic rover on Mars. So these are three most recent, this is 2021, I believe, 2020, this is 2021. So these are the rovers currently on Mars. So you see, even landing robotic rovers on Mars are highly risky, and there's no safe. There's no guarantee that you'll be successful. In fact, so many countries have tried, and only 2 have succeeded so far. Now, this is not to scale, but gives you a rough idea for a robotic rover landing on Mars, what would happen. I'm focusing on this phase. It's called the EDO, stands for entry, descent, and landing. That's what we are doing here. So basically, what happens when you get to Mars, then you start what's called the atmospheric entry phase. This is a phase you fly through the thin atmosphere of the Mars, which in the previous slides you saw that has 1/100th of density of the Earth's atmosphere. So it's something that's dangerous. It can create enough risk, but it's not enough to get the job done by slowing the vehicle completely down. So for robotic rover, you would have a parachute phase that further slow down the spacecraft, then comes down to power descent phase, where that's not quite enough. You have to still use some propulsive force to slow down the vehicle. Then you finally land on the vehicle, okay, on Mars. So this is how a robotic mission typically would do. Now, this slide shows the history of different sizes and mass and etc. on the U.S. Robotic rover. This is the one's 1976, 60 years ago, or 50 years ago. Up to most recent, this is 2020. This is Perseverance. So that gives you a number of a bunch of values. I want you to take a look among them. Take a look at the landing mass. The heaviest one that we have landed so far is about 1 metric ton. The next one is about 900 kilograms. Okay, that's when you land everything that rover on Mars. That's how much it weighs. And if you take a look at the parachute, these 2 missions are essentially the same. the diameter of the parachute is 21.5 meters. It's a huge parachute for that little thing, okay? Now, if we want to land, let's say, 2 astronauts on Mars, the landing mass will need to be anywhere between 26 to 36 metric tons. 26 to 36 more heavier than the heaviest rover we have ever landed on Mars. And for such a heavy vehicle, no parachute is big enough. Or you can make a huge parachute, but it takes very long for that to open. By the time the parachute is fully open, you already crash. So parachute is no longer a viable option. So we have no parachute in there. Okay. So you can see that if you want to land a human on Mars, or sometimes we call it high mass or human scale mission, it's not just a simple scaling up. Things would have to change differently. So what are the things that we are looking at? These are several vehicle concepts that configuration that NASA or industry are actively looking. These two are reentry vehicles that NASA has studied quite extensively for possible human mission. This one, it's actually a very interesting thing. You look at this. This is actually inflatable. Before it's deployed, it's all collapsed. Then you basically put the gas in there to make that in such a shape. So this is what's called the hypersonic inflatable aerodynamic decelerator, HIAD. So this is a very weird looking one. This is more or less a somewhat traditional aerospace entry vehicle shape, rigid body. Now the commercial space industry obviously is very much working on at least landing on the moon and beyond. This is Blue Origin's concept of the human lander. This is on the moon, and this is SpaceX's concept of the human landing system. They intended for both. If we still go to the moon, they intend for both moon and the Mars. So these are the different types of systems that have been actively developed. Now, what are the unique challenges for human-scale Mars mission? As I mentioned, your landing mass will be roughly 30 times more than the heaviest lander we have ever landed on Mars. There's no parachute that you can use. So something will have to be done differently. The way that we will do it differently is that right after the entry phase, you're not going to go through a parachute. You have to ignite a rocket. That rocket has to be ignited at the supersonic speed, roughly 3 to 4 times speed of sound, because that's where your entry phase ends, because the Martian atmosphere can no longer reduce the velocity below that. So at Mach 3, 4, you have to ignite a rocket that will slow this thing down and land it. And you need to land very accurately. We want it to be less than 100 meters or less, the precision. For a Mars mission, it is more than likely that you're going to have to land multiple lander on the same site, because one lander is not enough. So you could have a camp, okay? That makes the landing precision even more critical, because you definitely don't want to crash into other lander and all the structures, etc. So all this must be done autonomously. I remember the previous slides mentioned that it shows us that your time delay, communication signal delay between Earth and Mars could be 40-some minutes. up to 40-some minutes. There's no way you can control this thing from the ground. By the time you receive the signal, everything is already over. So has to be done autonomously. Not only that, you have to do that reliably in the presence of a significant uncertainty. By uncertainty, we do our best, but still we really don't know a lot of things on Mars, even our own system. We'll give you an example here. This is the Martian atmosphere density versus the actual density versus the actual density versus the model that we have. If everything lines up here vertically, that your density is the same as my model says. But you see, that's far from it. And anywhere, you could be easily 50% off. I'll give you an idea what 50% off means. The aerodynamic force is proportional to the density. So that means what you think you're going to have the force on the vehicle is 50% off. Well, but you still have to land me accurately, even in the presence of this type of uncertainty. That's very challenging. That's very challenging. So, give you an idea of what a 100-meter landing precision means. Back in the days in '76, the very first Mars robot rover that U.S. sent is the Viking program. Viking program has a landing precision of a 280 by 100 kilometer precision. This 280 means that's the semi-major axis of the landing ellipse. 100 meters is length of the semi-minor axis of the landing ellipse. If you land in this huge area, it's basically close from one end to the other, 560 kilometer. If you landed in that huge area, it's considered a success. Okay? Now, 20-some years later, technology got better. In the 1997 Pathfinder mission, we were able to do 100 by 20 kilometer. Okay? Then we'll progressively shrink this landing footprint down to 65 by 9 kilometer. That's 2024 Opportunity lander. We can no longer reduce that footprint. The reason being, all these missions or fly by, the entry is what's called the ballistic entry. It means is that it's more like a slingshot. You try your best to control your initial condition when you enter the atmosphere. Once you enter the atmosphere, there's nothing that controls the vehicle. It's basically fly a trajectory that's determined by the initial condition. It's called the ballistic entry. That you can do that only to a certain extent. That's the limit of it. You want to get even more accurate, you would have to accurately guide the vehicle, to control the vehicle during the entry flight. That's the first time it's tried in 2012 in the Curiosity. This is Mars, also known as the Mars Science Lab. This is the first time the entry trajectory is guided, actively controlled. So we're able to get down to 20 by 7 kilometer. And on 2027 Perseverance lander, we were able to guide the vehicle and make it down to 8 by 7 kilometer. Okay? That's still cross about 16 kilometer, 14 kilometer. So your worst performance, you'll be still 8 to 7 kilometers from the landing site. For a human mission, we want to land here, 0.1 meter, 0.1 kilometers, 100 meters. This is also, we call that pinpoint landing requirement. It's literally, in that scale, it's like land on the point of a pen. So it's pinpoint landing. That's the accuracy you need to have. The reason is very simple. When you are talking about the human landing, the astronauts need to be landed sufficiently close to the base or to whatever the infrastructure that's on the ground. There's no way you can hack 10 kilometers with all that equipment and everything, right? That's a life and death situation. So this is what we need to do. Okay, this is the sequel, or essentially the subsequent part of that video. We're getting to the get to the Mars now, and we're ready to do EDL, entry, descent, and landing. This is the entry phase. You still generate high velocity, high heat, even though the density is not nearly as high as in the Earth. Now, once you come out of the entry phase, there cannot be any parachute phase, so you're going to have to start engine right now. This is a huge rocket. Just imagine how much propellant it's going to consume in that power descent phase. Okay, we landed. So, what do we do at the San Diego State toward this, holy grail? We are working on what we call the focusing on the EDL phase. Like I said, the EDL phase is has a lot of challenges among many other technical challenges. And the engineer at the JPL coined phrase this term, 7 minutes of terror. That's because the EDL phase at Mars typically lasts 7 to 9 minutes. And in that 7 to 9 minutes, it's excruciating. You don't know what's going on. And you cannot do anything. You just hope all your hard work actually works. And you only find out 30 minutes later. Okay? All right. So this three phase has an entry from 120 kilometer velocity, about 4.7 kilometer per second, down to somewhere around 4 kilometer in altitude, maybe 500 meter per second, maybe 15 kilometer to the landing site. That's the end of the entry phase. Then you ignite the engine. That's where the power descent starts. You go all the way down to maybe 200 meters above the target landing site at 5 meters per second. Then you do the landing phase. All this phase, every one of these phases needs to be controlled very accurately to ensure a safe and precise landing. More than that, as I alluded just a moment ago, we really would wish the final power descent phase would use as less propellant as possible, because it's a huge engine. Every second it burns tens of hundreds of kilograms of propellant. Okay, it might be a good time to insert a quick anecdote. For those of you who, well, some of you may even aware, the Apollo 11 mission, when the astronauts first landed on the moon, because they had to do some evasive maneuver, the hazard avoidance maneuver, you probably have heard, when they eventually landed, the propellant margin was very uncomfortably low, meaning that if they had to go a little longer, they could run out of gas. And when you run out of gas, you can't just park the thing on the side of the road, wait for help. You're doomed. So we want this mission to use as, well, actually there's one more. Now, that is very well known, but very few people even knew that in the Apollo 14 mission, the propellant margin was actually even smaller than Apollo 11. But simply because Apollo 11 was the very first one, most people are aware of that. Not very few people aware that Apollo 14 came even closer to the edge. So all this makes that we really want this thing not only land there, we want to land it with the least amount of propellant, what we call the propellant optimal landing, okay? And that reason is very simple. We have demonstrated that if you fly identical missions, same vehicle, if you're using a propellant optimal scheme to land this thing, you could save easily for a typical human scale Mars mission, save up to 2 to 3 metric tons of propellant. Everything else being equal, you save 2 to 3 metric tons propellant. What that means is that you could, for the same vehicle, instead of carry the propellant, for the same margin, you could carry other things, life support instrument, maybe a couple more astronauts. So that's what the implication really means. All right? So, well, being an engineering professor doesn't feel right if I didn't show you any equation in this lecture. So here we go. But I also promise you this is the last slide that has the equation. This is basically the equation that describes what would happen during the entry. I mean, each phase would have these kind of complex equation. So I just want to show you that the physics are very complicated here. And this is the base that we have to work on. So what do we do at San Diego State? We develop the advanced entry guidance algorithm. So what is guidance? Here I give you a quick sort of a crash course. Guidance is really means, in aerospace sense, real-time determination of the maneuvering commands to steer the vehicle flight trajectory that satisfy all the mission objective constraints, etc. So guidance system, in a way, is the brain of the vehicle. Or put it another way, you have all heard full self-driving, FSD, electric car. Well, in aerospace engineering, that is still not quite made it yet, right? But in aerospace engineering, we have been doing that for 40, 50 years because we have no option. We cannot rely on supervised driving because no one can supervise these things. So we have been doing that for that long, and that's essentially what the guidance system of an aerospace vehicle is doing. At and particularly for entry flight, there are essentially 3 generations of guidance technology. One is the Apollo and the Space Shuttle, and the latest one is what's called the predictor corrector entry guidance algorithm. And we are the leader in the advanced 3rd generation entry guidance algorithm. This is widely recognized by NASA and any other stakeholder. And that is the algorithm that we develop. It's fully automated, widely applicable to essentially any planetary entry mission. Has been extensively used in all the number of projects and programs by NASA and the industry. So this is one of the major components that we at SDSU have been working on and where we are. The next part is this power descent phase. Get this thing up here. The power descent phase really is about the last one. I mean, we get close to. We're getting close to the ground, and believe it or not, the Apollo era power descent guidance still represents the sort of a standard that we are measuring up to all 50 years ago. So it also speaks to the ingenuity of the engineer at that time. But we are one of the 2 universities in the US that are developing the advanced power descent entry guidance that guides human scale landing mission, including Mars. And our algorithms not only can fully autonomously operating, it also is propellant optimal. The Apollo power descent guidance is not optimal. And ours is theoretically optimal. So meaning that for the same mission, same vehicle uses the least amount of propellant to land the vehicle. And our algorithms has been selected by NASA to be flight tested in the rocket lander. I don't know how. Yeah, here we go. This is the rocket lander that our algorithm will be flight tested. This will be in Mojave Desert, and if everything goes well, the flight test actually will be in about 2 weeks. So we'll keep you posted whether or not we were successful or we'll crash the thing. So this is where we are, and let me take a quick look at my time. What? I'm good? Okay. Okay, I have one more slide that I want to sort of instill you some weird idea that we aerospace engineers came up with, but all in the name of enabling a human scale Mars mission. Something called error capture. We talked about the EDL, but there's something that I didn't mention. That is, when you go from the Earth to Mars, when you arrive at the Mars, the spacecraft, you would be at a very high speed, typically 7 kilometers per second. Okay. For a human mission, most likely you want to slow down the spacecraft into a, let's say, orbit around Mars, and so that you can prepare a survey. When you get ready, you begin to land, right? But if you do that, that orbit typically only sustain a speed of 4.7 or 8 kilometers per second, and you come in at the 7 kilometers per second. What do? Well, you say, let me turn on this rocket and slow it down. Yes, you can do it. But if you do that for a human scale vehicle, you probably will spend up to 40 metric tons of propellant. Think about that. 40 metric tons of propellant just to slow yourself down. Once you're done, that's it. That brings nothing. Well, now we're thinking, okay, now we know the Mars has this is the atmosphere. Instead of directly going that, why don't we just, pass through it? If we pass through it, if we control the trajectory really accurately, we can get out of the atmosphere, and without very little help, we can put ourselves in that orbit around the Mars. Essentially, what's called propellantless maneuver. I mean, you do need a little bit propellant, But mostly, it's compared to, the 40 metric tons, it's nothing. So this maneuver, it's what's called air capture. You essentially fly through the atmosphere using the aerodynamic force to capture the vehicle and put it in orbit, all without spending that 40 metric ton propellant. That's a very much enabling technology. But it is also very challenging because, like I said, we don't know precisely the information in this atmosphere. If you are not careful and if your trajectory is not controlled accurately, what could happen? You could crash onto the surface of Mars, okay? Or you could skip out all the way to God knows where. So that's where the aero capture guidance and control becomes a critical technology. You really want to make sure that you fly through it safely, get to where you want. This is what we are working on, and we also have a guidance technology that's developed, and also it is also optimal in the sense that once you get out of the atmosphere, it allows you to use the least amount of propellant just to clean up the orbit. And so here's the trajectory that will show you what could potentially happen. This is where you come in at, from Earth. You arrive at Mars at upper edge of the atmosphere, around 6.2 kilometers per second. You control and guide the vehicle very accurately, flies through the atmosphere, roughly about a 40 kilometer altitude. During this phase, you basically deplete about 1.7 or so, 1.4 kilometer per second velocity, without spending a drop of the propellant. Then you come out of here. At that point, essentially, you're probably roughly here. You probably need a little bit burning of the engine to clean up your trajectory so that you can stay on this orbit. But that's how much it can be done. This is something that has never been done before. Has been studied many years. It hasn't been really flown. So, but we have a reason to believe that we are at the cusp of a major development that could potentially make that become a reality, and our algorithm is going to play a central role in that effort. So that's what another layer of things that technology development that we are involved. With that, I guess I'm going to conclude my presentation. Again, the human space, we have reason to believe human space exploration will see major activities in the coming time. It's not, the multiple spacefaring countries are pursuing this, US, China, and other countries. And we're really in a time where this will become very much a negative period. And human mission to Mars is going to be likely a really focal point, okay? So we are at the San Diego State, at least in the areas that are working on, is at the forefront of the development of advanced and enabling EDL guidance technology for a human-scale Mars mission. So it is an exciting time. It is an interesting time. With that, I conclude my presentation. Thank you.
That was fantastic, and thank you so much for your presentation. For those of us us who are not engineers, I understood what you said, so that's always a good sign. And very interesting and certainly opens our mind to the future. And you'll see from all the things that I said at the beginning, these are, when we award these distinguished professor, it's not only about the history, what people have done, but where they're going, and you saw that last component, all the possibilities that still lie ahead with the work that you're doing. Before I open it up to questions from the audience, I wanted to say a couple of thank yous. A thank you to our nominees. Nominators, I should say. We had a significant, this was the highest year since I've taken this role of nominations, which is testament also to you to have been selected by our committee. A big thank you to the committee for their work reviewing these outstanding applications and being able to make a recommendation, because it was certainly a difficult year with the many applications that they got. And that goes along to also all the outstanding scholars, awardees today and their nominators. We had an outstanding pool as well, and it's really lovely to see the campus coming together to recognize their colleagues. So thank you to everyone who contributed, to Mark and his team who put this event together, Sarah, Stephen, and all the other people who are not even here. So I really appreciate all the work that goes behind the scenes for you to be here today.
Can I say a quick word? I didn't notice that, but I want to recognize my former PhD student, Sergio. Sergio, stand up. I didn't know that he's coming. He works at NASA Johnson Space Center, and so I'm happy to see him here.
That's wonderful.
Yeah.
Yep. So now it's our Q&A session. We're opening up to the audience. I'll moderate, and here we are. Eugene's leading us off.
A really fascinating topic and great and very inspiring talk. So my question is it helpful in any way that this is a human involving mission for the entry guidance or guidance at all, or the presence of humans is just a disturbance, a challenge?
You're absolutely right. Unfortunately, the answer probably is the latter, because at that high speed, no human, it is not humanly possible, let's say, to react, to control, to handle everything. So it has to be autonomous operation. Human would be a could be a supervisor toward the end of that power descent phase, where you're getting close to the landing site, and you could help identify whether or not there's a hazard, or do I need to make some select a different landing site. That is at a relatively low speed region, and the human can get involved, certainly. Not during the entry phase, where you're traveling at 4.7 kilometers per second. You move your finger, you're already off like 100 meters. Okay? No, unfortunately.
That talk was very exciting. I'm just curious,
Why have you moved?
Oh, let's start this one then. This one's working.
why have you moved away from the other shape of lander? You had shown the two shapes before, the one that's more bullets and then the one that had like bumpers on it, it seemed like. And why, is anybody considering a combination, and why did y'all choose the one shape over a different?
There's a lot of consideration that actually goes into deciding which configuration you want to choose. For instance, the two that I showed you, the one with a flexible, inflatable structure, that one has a clear advantage that when you send the vehicle to Mars, you can pack it. Yeah, it's very compact, and by the time you get close to it, you inflate it, and so that's the advantage. On the other hand, we have more engineering knowledge and legacy technology to support rigid body design, the second one. So, Also that involves the subsystem. I mean, you know that weird shape. How do you going to put your astronauts, and when you go through the atmosphere, what's the thermal protection? All these things will become a consideration to eventually decide which one you're going to go for. So it's really quite involved. It's no less than designing a very advanced aircraft, perhaps even more. So that's a job that will need to be done. I mean, a decision will have to be made sometime, but at this point, these are the competing concepts. Eventually, who wins out remains to be seen. Thank you.
For error capture to be implemented on a Mars mission, I understand it could save a lot of time for a Uranus mission, like multiple years. Could it be the same for a Mars mission? If so, how much time could...
Possible. I mean, the reason you say you say that error capture could save time is because you can fly faster. I mean, especially if you have a more advanced propulsion mean during that 6 or 8 months travel, typically that's what we call. But if you have a propulsion system on board, you can keep accelerating the trajectory. So you travel faster, you get to Mars quicker, right? The downside is that you get there with higher velocity. And same thing, since you get there with higher velocity, you need to find a way to deplete those velocity. Well, then error capture becomes a really, I say, propellantless way to reduce that. So yes, it's either allows you to go faster, travel, have a shorter travel time, or in the regular travel time, you still save that kind of a propellant to slow this thing down, even without additional acceleration. So yeah, either way. Yeah.
Professor, I just wanted to say, first of all, it was a lovely presentation. Congratulations on your award. My question was, if, as you said, we can't have a big enough parachute for one, but we use multiple smaller parachutes.
The same thing. You have multiple parachute. You got to be very careful. They could tangle. Okay. Every one of them needs to be big. And now you have a multiple, and that I have not worked on parachute, but my intuition probably tells me it's even more complicated. I'm not sure you want to go there because a multiple parachute, if any two of them tangle together, that's really very disastrous.
Well, first of all, thank you for the presentation. It really gave a lot of insight on where we stand on Mars. So you showed in one of the slides the uncertainty on the density prediction with altitude. So is that mostly a question about if you don't know the constituency, or is the problem with pressure and temperature?
No, you're right. The second part is more relevant. There are so many factors that influences the density, the atmosphere density at any given time. Not only depends on altitude, location, season, date, dust storm, whether or not you have a dust storm, the strength of a dust storm. There are so many factors that will impact the air density. That's why you never know which one you're going to run into. Yes?
Hi, I have a question about when you think of the reliability aspect of propulsively landing. The examples you've shown are like Starship, which uses turbopump rocket engines. These would have to be reignited after like 7 months in space.
Yeah.
And I just wonder what you think.
Well, that's a very, are you with Rocket Club or something? That's a very pertinent question. Yes. You will definitely want to make sure that your propulsion system can reignite, and because there's a phase that I did not talk about. unlike a rover or robotic mission, any human scale mission will involve an ascent phase. You're going to have people back, right? And so that is one of the technical challenge that the people are working on. And I'm personally, I'm not working on that, but I know people are fully aware of the situation, the challenge that you're talking about. We want to make sure when you punch out, you do go out. Okay, thank you.
Hi, Professor. First of all, great lecture.
Thank you.
So one of the questions, or one of the thoughts I have thought about the actual landing on Mars is, have anyone or have you thought about like something like a aerodynamic assisted landing, such as like a fixed wing landing they might see on the shuttle, even though if the atmosphere is much thinner on Mars than we know, and there's no paved ground, so there's a challenge with that, but is there like a...
Absolutely. You're talking about the airplane landing. I think the challenge, definitely one is that since you are only 1/100th of density of the Earth, you need the surface area, reference area, to be 100 times just to generate the same amount of aerodynamic lift. That certainly is one, because the size is big limiting factor. I think the other thing is the infrastructure. Until somebody puts a runway in there, the very first one cannot be a plane landing, plane type of landing. But in the future, once you started the base, and it is not beyond beyond imagination that you potentially could have something like that, but definitely not at the beginning. Yeah.
Here. Oh, so it's so motivating to listen to all the talks, and particularly I wish everybody knew the impact that it has on the field of guidance navigation control. Everywhere you go, people know these things, and the things you do. That's incredible. And I guess one thing I always see is just you dominated the field of entry, you dominated the field of power descent, you dominated the field of aero capture. Do you have any plans of dominating the field of ascent?
Ooh. That's a really good question. Go for it.
Oh yeah. Yeah. Well, that part we actually are very much working on that. Yeah. Thank you.
Somewhat related. A few years ago, I was serving on these NASA panels and selecting chemistry instruments for rovers.
Yeah.
All the rovers, and we consider all kinds of energy sources. Nuclear energy is one of them.
That's right.
Air capture is wonderful, but is nuclear still an option?
Nuclear would still be an option, but any nuclear power tends to be used in the situation where you have more time. I mean, it's not something that you can use that for a high impulse type of situation, like what we're talking about. But nuclear propulsion is very much in play, like the question that was raised a moment ago. You could have a nuclear propulsion system during the flight from Earth to Mars that constantly accelerating you. Its acceleration is small, but over time, it actually builds up your velocity appreciably, get you very, maybe, let's say, cut your travel time by half. That will be tremendous, because one part we have not talked about is that long duration human space travel will be a very severe challenge. Okay, not only we have not have that kind of travel, but if you can shorten the time by half or even more, then all of a sudden we're within the limit where we have experienced, on the space station around a year or so. That we have pretty experience. So yes, nuclear propulsion, nuclear type of energy, potentially again on the ground, that could be a power generation technology for sure. Because if you're human there, you need power 24 hours or the whole day, whole Martian day. So power generation could be, but for very high force and short duration application, I don't think we are there yet to use nuclear generator power to do that sort of thing.
Thank you so much for your time, for your thoughts, for your dedication to San Diego State and your field. You're an example to all of us of how a faculty should be at San Diego State. So we appreciate all your time. Here's a plaque on behalf of the university. Thank you for having us. Is about to start. Please join us to celebrate him and all of our outstanding scholars. I would like to ask them to join me in a picture with me, and maybe, did you leave? Oh, okay. Garoma, do you want to say? Oh, the Garoma leave too. Okay, so your dean's office is not here, sorry. But we'll take a quick picture, and then the rest of you go ahead and enjoy the reception. Thank you all for joining us, and congratulations again.